In today's topic, we're talking about the speed of sound as well as the speed of light and what happens as materials that they are trying to pass through get increasingly more dense. If we're talking about the speed of sound, we've already talked about the fact that as the temperature goes up, we had said that the particles move faster, and since sound waves have to move from particle to particle because it is a longitudinal wave and there's compression involved, we said that as the temperature goes up, the speed of sound is going to go up because the particles are moving faster. The same thing is going to happen as you start packing those particles closer and closer together. Again, if you've had a good chemistry course, or if you probably learned this in a physical science course back earlier in your science career as well. In a solid, your molecules are packed the most closely together of all three states of matter. In a liquid, they're a little bit further apart. They're they're moving around, they're moving past each other, but it's not as close together as they are in a solid. And in a gas, the molecules are the furthest apart still. And so therefore, the speed of sound actually travels faster in a solid than it does in a liquid, just because the particles are closer together. And it's going to travel faster in a liquid than it is in a gas, again, because the particles are closer together. And so it's easier for that energy in that longitudinal wave to jump from one particle to the next. However, in a longitudinal wave, you also have to be able to compress the material. And so as what's actually true is that as the density of something increases, the speed of sound is actually going to go down, because if you can't compress the material, the wave has a lot of difficulty moving through there. This is one of those situations, though, where one factor tends to play a much bigger role than the other one. And with the speed of sound, as it's concerned, the fact that the particles are going to be closer together in solids than they are in liquids and gases is going to be a much more important factor than it is as far as the overall density is going to be concerned. Now, just the opposite is true of light waves. For light waves, which are transverse waves, as the density increases, the speed of light is going to go down. And so while for the speed of sound is fastest in a solid and slowest in a gas, it's exactly the opposite as it is for light, because for light, the speed of light is fastest in a gas and it's slowest in a solid. So they're just the opposite of one another, okay? The example problem we're going to work together today is example 11.3, where we're kind of combining some information about light and sound together. And that's in the case of a thunderstorm. I think I mentioned in the last video that we have a lot of thunderstorms here in the Midwest, and so this is something that we're very familiar with. I don't know if that's the case where you live or not, but this problem here says a physicist is watching a thunderstorm. She sees a flash of lightning, and then here's a thunderclap 1 second later. If the air temperature is a cool 15 degrees Celsius, how far away from the physicist was the lightning formed? So if I look at what I know in this problem, I know that the time it took for the sound to travel from when the lightning hit till the time she heard the thunderclap was 1 second. And I also know that the temperature was 15 degrees Celsius, okay? And so what I'm asked for then is how far was the physicist from where the lightning flash happened? Well, I need to know two things. The first thing I need to know is, first of all, is how quickly is this sound wave even traveling? And the way I'm going to figure that out is by using the equation that we had earlier, where V equals 331.5 plus 606 times the temperature, and then that gives us an answer in units of meters per second. So what I'm going to do here then is I'm going to have 331.5 plus 0.606 times the 15 degrees, and that will give me a speed of sound of 340.6 meters per second. So that's how fast the sound is moving. Now, how am I going to figure out how far away she was from it? Well, if you remember from the very first module we were doing, we talked about how speed is the same as distance over time, or in your book he uses the fact that that you've got distance equals speed times time. So distance equals the rate times the time, which is something that, this is the way that you tend to see it in algebra class. It doesn't matter which one you use because you're going to get the same answer either way. They're just the same forms or different forms of the same equation. So if I use my speed equals distance over time, I know that the speed of sound is 340.6 meters per second. You'll notice I'm kind of interchanging speed and velocity here. The speed of sound isn't really going to be affected by, it's not going to be go around any curves. It's going to be a straight displacement. So in this case, I can use them interchangeably because the distance being traveled is actually a displacement as well. So the distance is what I don't know, and the time is 1 second. And so what that tells me then is that my distance is going to be 341 meters away. Right, so you'll get some practice working some of those problems today.